Welcome back to our explainer on Module 6. Up until now, we've really just looked at reactors existing in a perfectly happy, steady state. But in the real world, a reactor has to start up, it maneuvers power for grid demand, and it constantly responds to temperature shifts. So today, we're translating the complex mathematics of reactor kinetics into what is essentially a high-stakes story about a ticking clock. We're looking at the raw physics that stand between a safely controlled power plant and an uncontrolled energy release. So I want you to put yourself right in the operator's seat for a second. Let's ask the absolute most critical question you will face in that room. When reactivity changes suddenly, does human intervention even stand a chance against nuclear physics? I mean, are we talking about a response window of minutes, seconds, or mere milliseconds? To answer that, we're going to track the clock through 5 distinct phases: time and reactor kinetics, the math of control, the delayed neutron miracle, built-in safety feedbacks, and finally, the decay heat challenge. All right, kicking things right off with Section 1, time and reactor kinetics, specifically looking at the prompt jump. Like I mentioned, previous modules looked at perfectly balanced, stable reactors. But kinetics? That is all about dynamic change. It's the study of how the neutron population, and therefore the reactor's power, shifts over time. Kinetics answers those absolutely crucial what-if questions. If you insert negative reactivity, exactly how fast does it shut down? And if you accidentally insert positive reactivity, exactly how much time do you have to fix it? Well, the math behind the initial power spike is incredibly fascinating. Imagine a steady reactor, and suddenly a control rod is withdrawn. In those very first microseconds, literally before any delayed neutrons can even factor into the equation, the neutron population adjusts almost instantaneously. We call this the prompt jump. If you insert positive reactivity, prompt neutrons cause an immediate power jump governed by this formula, where rho is the inserted reactivity and beta is the delayed neutron fraction. To put that into perspective, a 50-cent reactivity insertion immediately doubles the power. And the scary reality? There isn't a mechanical control system on Earth that can prevent it. And just to really hammer home how fast we're talking here, if a reactor relied on prompt neutrons alone to maintain its chain reaction, a tiny 10-cent reactivity insertion would give you just 15 milliseconds to respond. 15 milliseconds! That is a speed at which no human, and honestly, no automated control system could possibly react. The reactor would be entirely 100% uncontrollable. Which brings us nicely to Section 2, the math of control equations and reactor period. Because obviously, we do control them. So how does that work? The mathematical framework we use to manage this immense energy is called the point kinetics equations. Now, these are formidable equations, but they actually simplify the entire reactor down to a single point, basically ignoring spatial variations in the flux. And yet they capture the essential time-dependent behavior with incredible accuracy. You've got one equation tracking the net production of the overall neutron population, and then 6 distinct equations tracking the delayed neutron precursors, one for each recognized decay group of uranium-235. Now, out of all those complex equations comes what is probably the most practically useful metric for an actual operator, the reactor period, denoted by the letter T. This is simply the time it takes for the reactor power to change by a factor of E, which is roughly 2.718. It's pretty straightforward. A positive period means rising power, a negative period means falling power, and an infinite period means power is perfectly stable. Operators are monitoring this continuously. If that period drops below about 30 seconds, alarms are going off. And if it drops below 10 seconds, boom, you get an automatic, immediate trip of all the control rods. And this right here brilliantly illustrates the in-hour equation in action, which links reactivity directly to this stable period. Notice how just a smaller reactivity input dramatically lengthens your stable period. A massive $1 input gives you a genuinely terrifying 5-second period. But a 10-cent input, that gives you a nice, stable period of about 150 seconds. This mathematical relationship right here is exactly what buys the operator precious time to maneuver the power safely. Moving right along to Section 3, the delayed neutron miracle, or as I like to think of them, the heroes of the story. Because let me tell you, delayed neutrons are the absolute heroes of nuclear engineering. In a critical reactor, prompt neutrons alone actually aren't quite enough to sustain the chain reaction. The deficit is made up by these delayed neutrons arriving from precursor decay. Because we have to wait for them, the overall mean generation time of a neutron is extended by 4 orders of magnitude. It stretches from a microscopic fraction of a second to about 0.1 seconds. That simple delay literally turns a 15-millisecond disaster into a 2.5-minute window of complete control for that exact same 10-cent reactivity insertion. As our source material points out, delayed neutrons aren't just some minor math correction in the kinetics equations. They are the fundamental physical phenomenon that makes nuclear power possible at all. Their existence is quite literally a fortunate accident of nuclear physics, upon which the entire engineering framework of reactor control is built. So let's look at Section 4, built-in safety feedbacks, how the machine responds. Beyond just the physics of the neutrons themselves, we have to look at how operators effectively monitor the reactor and how the core naturally defends itself from any power excursions. Even when completely shut down, a subcritical reactor still produces a measurable neutron signal. So, during a cold startup, operators methodically follow this sequence. They withdraw the rods in tiny, careful steps and plot the inverse of the subcritical multiplication factor, the 1/m plot. As they add reactivity, this line should extrapolate cleanly to 0 at the exact moment of criticality. This deliberate, step-by-step procedure ensures there are absolutely 0 surprises as the machine wakes up. But tracking all of this requires some pretty incredible instrumentation, because the neutron flux in a reactor spans an astonishing 12 orders of magnitude. From cold shutdown to full power, you can't just use one detector to do the job. Instead, operators rely on 3 deliberately overlapping detector ranges. And that overlap, that is a strict safety requirement. The source range must still be reading meaningfully when the intermediate range comes online, and so forth. It guarantees operators maintain a clear, unbroken line of sight on the reactor's behavior at all times. But, okay, what if reactivity spikes unexpectedly? Well, the core actually protects itself within milliseconds through the Doppler effect, which is also known as fuel temperature feedback. Basically, as the uranium fuel heats up, the thermal motion of the nuclei causes the uranium-238 resonance absorption peaks to broaden. In plain English, the hot uranium essentially swallows up more neutrons, which immediately drops the reactivity. It's a totally inherent, universally negative feedback loop that safely limits power excursions without a human having to do a single thing. All right, finally, let's slow that clock all the way down. Section 5, the decay heat challenge, the long tail timeline. The critical takeaway for this whole section is that a reactor cannot simply be turned to 0 like a light switch. Even after the control rods drop and the fission chain reaction immediately halts, all those radioactive fission products that accumulated in the fuel during operation, they're still sitting there, and they continue to decay, releasing immense energy as beta and gamma radiation. This is what we call decay heat. The very moment a reactor shuts down, decay heat immediately accounts for about 7% of the pre-shutdown power level. Now, 7% might not sound like a ton, but if you have a reactor that was operating at 3,000 megawatts thermal, the exact second you hit that shutdown button, it is still generating 210 megawatts of pure heat. That is definitely not negligible. It is more than enough to completely melt the nuclear fuel if active cooling is somehow interrupted. And decay heat follows a really brutal power law. It drops off pretty significantly at first, having it just a minute, but look at the long tail on this timeline. After a day, a week, even a whole month later, it is still generating a fraction of a percent of that massive pre-shutdown power. It never just immediately reaches 0. It requires highly reliable, continuous cooling for months, sometimes even years, after the reactor is supposedly off. And this isn't just theory. The 2011 Fukushima Daiichi disaster perfectly and tragically illustrates this exact physical reality. When the earthquake struck, the kinetics equations worked exactly as intended. The reactor shut down automatically, K fell below 1, everything worked, but the subsequent tsunami disabled the emergency diesel generators that were powering the coolant pumps. So while the active chain reaction was stopped, the total loss of those cooling systems allowed the relentless decay heat to literally melt the fuel over the coming days. It's exactly this engineering reality that led to modern reactor designs prioritizing passive cooling that doesn't need any pumps or power to operate. So I want to leave you with this incredibly chilling realization from our source material about the true nature of reactor kinetics. The chain reaction had stopped. The kinetics problem had not. When you shut down a reactor, do you truly have it under control, or does the clock just keep ticking? Something to chew on as you review these point kinetics equations. Thanks for hanging out, and we will see you in the next explainer.